Welcome to the 5th practicals of Introduction to Structured Programming. Today, Tanya and me will do the practicals, and Julia sitting here in the first row and will correct us if we make any mistakes. Okay, then let's see what is our plan for today. We will start off with some organizational matters, and then we come to the interesting topics. So the first part is multiple files in C, and we will discuss this because you need this in assignment 2, which you have probably noticed already when you read through the assignment description. And then we come to the funny part, but very, very tough part of today's practicals. We talk about pointers, and we talk basically about everything that is related to pointers. So this is really, really an important practicals now. And yeah, we really try also to visualize everything that you can do with pointers, and hope that this is a good addition to the lecture from the last time. Then we'll also talk about strings a bit. And yeah, Tanya, you prepared the string literals because many of you used that in assignment 1, and we're not entirely sure if you are aware of what you have used there. So we try to explain it to you. And then we also talk about the user input and yeah, the most important functions there, and maybe if time permits, we also have an example there.
Yep.
So then to the boring part at the beginning, but also important part, there's just one organizational stuff happening today. So today the coding session 2 registration starts. So you have roughly 10 days to register for the coding session 2 until Sunday in a week. So please select your time slot, and then the corresponding homework will be available within the next days, so latest by Monday. And it's all about computational thinking and algorithms, so you can already apply the knowledge that you have got so far in the course to solve easy problems with the stuff that you have learned. Okay, then to the first real topic.
Then let's get started with multiple files in C. So first of all, let's ask ourselves, why would we need this? Why do we want to use multiple files for our program? So it wasn't that obvious yet in assignment 1, because assignment 1 was, of course, just a bit shorter, but programs can get really long, especially if you have a lot of functionalities, you want to do a lot with them. And having all of that in a single file will get really annoying to scroll through. It will be annoying to keep track of functions, fix something if something goes wrong. It just gets annoying to handle and hard to maintain. So that's why we can split our function definitions if they have a common theme off into their own source file, so the .c files that we've used up until this point. And we can also put their respective function declarations. So think back to forward declarations that you may have used already in assignment 1. We can put those into a header file. So the header file just contains the declarations, so kind of like the signatures of the functions that our program has, and the C files then actually have the implementations of those functions. And as Michael has already said, we do have a .h and the .c file in our assignment 2, which is the framework.c and .h. So you will need this knowledge if you want to use the framework correctly. So let's briefly talk about header files again. We've already heard about the hashtag include that we use to include libraries that we want to use in our programs. And basically with header files, we also just include header files in other .c files in order to use their functionalities. So we can share declarations between files, and we can include another header file with hashtag include filename.h. Do mind the double quotes we have here, because we don't have our, I don't know what the brackets are called, but the other brackets that we use for libraries, we use the double quotes here.
Angular brackets.
Angular brackets, okay. Okay, yeah, and the ending is .h for header files. Only declarations, not definitions, I already said that. And for compilation, since we have multiple files now, we can't just mention a single .c file in our compile command anymore, as we did in the past. So now we need to specify all the C files that we want to be compiled by our compiler. So we can do that by, for example, just listing each one of them. So if we do clang main.c and file1.c, because those are the two C files we have, then with the -o compiler flag again to name our binary. Or we could also do clang and then an *.c, which basically just means please compile all .c files you can find in the current directory you're in. And again, the -o. One thing to note here is that header files themselves are not compiled, but they're just included in other files. So that's why we only need to mention the .c files here, and we sort of like establish the connections between our files through the header files themselves. This will make more sense when I show you in an example, but let's just accept that for 2 more minutes. What is also important with header files is that we use header guards, because we could potentially include a header file multiple times if we have one. But including it multiple times would also mean that each time we include this file, when we actually compile everything, the compiler just kind of copies what we have in the header file into like the entirety of the code that it compiles. So if we include it multiple times, we have function signatures that are just double. So C is going to complain, wait, there's like multiple redefinitions of like the same function here. I don't understand what this means. So that would lead to errors and compiler errors and all that. So that's why we use header guards. So this is an example of such a header guard. At the start of a .h file, we can just use this if and define with some type of name, hashtag define with again some type of name, and then the end if. And in here, in the header content, we basically put all the function signatures we want to be part of this .h file. And then we can prevent it, if we include this file afterwards, we can prevent it from being included multiple times.
So if this was maybe now too much regarding the header guards, you can at the moment just accept that they exist and that you need to write them always in the H file, as we will do in a few seconds in the example. And you will learn in the next semester in much more detail why this is used.
Yeah. Mm-hmm. The most important thing for now is that you know how to include the file. You don't actually need to write this header guard for the framework in A2. That's already been done for you. All you need to do is to basically just include the file that's already there, which we're going to have a look at now. This also needs to be mentioned. A lot of you are not going to know what pragma_once even is, but it also needs to be mentioned at this point. This hashtag pragma_once does something very similar to the if and define of the header guards. But what's important to know about that is that this is not standard C, actually. So what this means is that the hashtag pragma_once basically just isn't supported by all types of compilers, while this if and define is kind of required to be supported by all types of compilers. So just if you decide to do one of the following assignments, if you decide to split it into multiple files, please use this if and define and not the pragma_once. That's all we have to discuss about this for now.
So then look at an example, I would say.
Yep,
yeah?
Let's go to the example. So we have our bits example from last week. For those of you who weren't here last week, quick recap. We read in a decimal number and we transformed it into its binary representation. We used 3 functions for that. What the program did isn't important for now. All that we need to know is that we want to put this getIFBit function that we defined here in this program, this bits.c file. We want to outsource that into a framework now and just use it in our bits.c program. So what we can do for that, I created an empty framework.h file here. As you can see, there's nothing in here yet. In the framework.c, we also don't have anything in here yet. So the way we start is that for this framework.h file, we create our header guard. So we have the, whoopsie, that's not the correct one. So we just type, as we said, the if and define framework H.
You usually use the file name for this constant that you're basically defining here.
So
and you write then everything in between, yeah?
So this is the header guard that we've defined now, and now we mentioned that we just want the signature of our function in the .h file, which means we take this forward declaration, we just cut it out, we go back over here, and we just paste that in. That's the first step. Now we still have if we scroll down here, we still have the definition of our function, or the implementation of our function down here. So we also just take that, cut it out, go over here into the framework.c file now, because we said the implementations go into the .c file. We put that in here. What we also need to do now is we need to include the framework.h file here to establish the connection between the .c file of the framework to the .h file. So the compiler can find, oh, what is the signature of whatever function we have here? Oh, that's this thing we have in here. Okay, I understand. So that almost works already. So we've completely removed the get ISP implementation and the forward declaration from our initial program. And all we need to do in here now is that we say hashtag include framework.h, as we also did over here. And as you can see, the function is still being used here. And now we can just go ahead and compile this entire thing. Actually, is that going to work now because I have multiple? Oh, no, that's not going to work, right?
Okay, you did. In this case, we have now like 5 C files in the folder and they are not connected, so it doesn't make sense to compile all of them. That's why Tanya needs to write now explicitly the files she wants to compile. So this works now.
Mm-hmm. And then we can just use our program again like we did last week. Just to show you one more time what difference this makes, if we were to comment this out, this include up here of the framework.h now, then we're sort of severing the connection of our program with the actual definition of the function. And if we now try to compile it, we will get a compiler error that you will be able to see in a second. Yeah, call to undeclared function, get ISP. We don't know where this is from. And as soon as we include the framework.h file, it's going to compile without an issue. So basically, this is what you have to do in order to use the framework in I2. But we also explained like everything around that, so you don't just blindly use the include and just keep rolling with it. So this is basically what's behind that, the header guards and using multiple files. This is how you do that.
And it's also important that we compile both C files. If you could show what happens if we forget to compile the framework.
Mm-hmm.
And then it states here, okay, undefined reference to get ISP in the
get binary representation function.
And this is basically because we have included in the framework.h that there exists this get ISP function, but we have never seen the compiled function or the definition of the function, because this is contained in framework.c. And if we don't compile framework.c, what should we do in this function? Yeah, so we really need to specify framework.c as well, such that also this code gets compiled and then can be used within our program.
Perfect. Are there any questions on that? Doesn't seem to be the case. Then I think we can continue.
Yeah, this was the easy part now of
now we get to
practicals.
Now we get to the fun part. Strap in, everybody. We're getting to pointers. So, quick recap. What are pointers? So, a pointer stores the memory address of another variable. You've already heard that in a lecture. And we're also going to discuss what an array is. So let's also mention that here real quick. with an array, we can store multiple elements of the same type in one big block of memory. For now. Technically, that isn't right anymore with dynamic memory, but that doesn't matter for now.
Yeah, okay. Then we would like to introduce our family now with what we're working today. Yeah, maybe go to back to the slides.
Back to the slides?
Yeah, I have. Ignore that there is some code below. That's for you then in the handout. So let me first switch the mouse to a pointer. Okay, this is the first step. Okay, yeah, what do we want to have in our main function? 2 variables, 2 pointers, and an integer array. Yeah, then switch to the code.
Then we can already switch. Yep.
It's a bit larger for you. This is already what we have prepared.
Just let me get to the correct one. This is the correct one.
Okay, yeah, so we have the integer x, the integer y. That is business as usual. Then we have created the pointer variables, pointer x, and we have initialized it with the address of x. As you said before, pointers store addresses, so we take the address of x and store it in the variable pointer x. Then we do the same thing also with pointer y. And then we additionally have these array numbers, so this should be also familiar to you. Okay, so basically that's it. And now we would like to introduce how we can actually visualize this. And we'll do this now step by step. So at the very beginning, we have just the x and the y variables. And in this case, we said we had this stack where all the variables are located. Then we have for each function such a stack frame. And in the stack frame of the main function, we start off by having a variable x, which has the value 2 in the beginning of the program, and then we have the variable y, which has the value 3 in the program. That is everything known. Let's have a look on the pointers that we additionally have. So we have this pointer x. So this pointer x is the variable. The content of the variable is this blue thing here, which is the address of something, and in this case we initialize it with the address of x, and that's why we have here address of x, and we draw an arrow from pointer x to the variable x. And then we have the same thing also for the y, so also y is a pointer, it stores an address, and also here we have the arrow to the variable y. And then the last thing that we have in the main function, as we said before, we also have an array. So this is the array numbers, which can store 4 elements, 0 on that at position 0, 1, 2, 3, and we filled it in with the values 1, 2, 3, and 4. So this is the content in the memory of the main function. So everything is stored there. All the variables that we've created are stored in the main function. Okay.
And now we will have a look at what the difference between call by value and call by reference is, because that's an important concept to understand when working with pointers. So call by value means that we pass a variable to a function in a way where the function gets a copy of the variable's value. So if we modify this copy inside of the function, we don't change the original variable, and we basically just have 2 separate copies of that variable in our program. One from, let's say, for example, the main function, and then we have some second function where we passed this copy to by value, and then we also have the existence of this copy inside the other function. Now with call by reference, the function actually gets passed the address of the original variable, which means that if we modify it in the function, it also directly changes the original variable, and we essentially just have one variable in memory. And this is exactly the type of concept that we need pointers for, because pointers store such memory addresses, and we can use them to pass things to other functions by reference. So we will show you a few variations of call by value and call by reference with pointers and array and all that. through a little example with a swap function, which means we create variables in main. You've already seen what variables we have created for that purpose. Then we will swap two of these variables in a function. And we then check what this swap operation in the other function changed in our main, which, as you can probably guess already, is going to look different depending on if we pass things by value or if we pass things by reference.
So then let's start with a very, very easy example.
So we already have the program here with the variables Michael already explained to you, and we now want to call this swap function that takes two parameters, which we will just give our x and y variables. So let's write that function now. It will just be a void function that takes two integers that we will just call a and b. And in order to swap these values around, we also need a tiny temporary variable, so to speak, which we will just, against style guide guidelines, but this is the practical demonstration, so it's fine. We'll call it integer temp, and we will save the variable, the value of our a in here. Then we will set a to the value of b. Then we can set b to the value of temp. So just to go into a bit more detail here, what we just did, we pass down here, if we comment this out again, we pass here as the first parameter our x, which has the value 2, which means we save the value 2 in this temp variable. We then overwrite the 2 that's in the a with the 3 that's in the b or the y that we pass as the second parameter. And then since we have still saved the variable the value that we had in a, we put that into the spot where we had the 3. So basically we just, as the name suggests, swap the two variables around. Yeah.
Okay, and at the end you print.
Then we print this little text down here.
Maybe we ask, so do we do an actual swap? So in the print statement here below, will the output be that x is 3 and y is then 2? Who thinks that this is the case? Who thinks that it remains the same? Okay, let's
have a look.
Okay,
yep.
You were right.
You were right. This is just a call by value once again, because this is basically what we've done up until this point, because we didn't have pointers at our disposal. We just passed directly the values that we have in here in x and y to our function and created a copy of them, which we will also be able to see in a second what that looks like in the visualization.
Mm-hmm. So if you look at this now, so the main function part remains now the same. And when we call the swap function in the stack, so actually below here, but I don't have infinite space below, so I put everything which is below here on the right-hand side. I create a new stack frame for the swap function, and in this stack frame, the local variables of the swap functions are contained. This includes the two parameters. So the parameters were a and b, and a received the value from x, that's why we have the value 2 here. Then b received the value from y, so this is the value 3. And then the temp variable got initialized to a, so this is also the value 2 then. And you can already see that on the left-hand side, the variables x and y are completely different from the variables a and b, which are now in the drawing on the right-hand side. And if we do now the swap operation that you described, then basically we swap here 3 and 2. So we changed the two values on this side. On the left-hand side, nothing changed here. X and y still have the same values. And when the function swap terminates then this part is not used anymore. The swap function doesn't exist anymore. Also, the changed variables disappear, and everything of the main is left, and here we didn't perform any changes, so we didn't do the swap. Okay, you said now, okay, when we want to swap, we need to use the pointers and the call by reference. So let's try to do this maybe.
Yeah. So all we need to change for that is that instead of just passing an integer up here, we can add our little pointer stars. And we've already said that if we have pointers in here, we could also say, doesn't matter which side you do the pointers on, but I'll do them on the left. If we have pointers in here and we said, okay, let's switch pointers around, let's do the temporary also as a pointer. So that's all we need to change in here. And then we also already have 2 pointers down here, our pointer x that carries the address of the variable x. So it's pointing at this variable that has the value 2. And the pointer y, which does the same, but it's pointing at y with the value 3. So now let's just try to give our pointers to this function, since we changed the parameters up here to pointers as well. And now I think that should work, right?
Yeah, let's ask
work,
again.
right?
Maybe we show again the print statement as well, so that we can see everything. Yeah. So now who thinks that we don't do a swap, that everything is the same? Who thinks that we actually do the swap now? Huh?
Okay, seems to be quite equally torn.
Let's see.
Let's reveal what it does. Well, that wasn't swapped.
Yeah.
But why?
Okay,
Why?
then
What happened?
let's look at the visualization.
The visualization will be able to tell us, hopefully.
What did we do? Yeah, we changed now the parameters a and b to be pointers. So these parameters will store addresses, and we passed pointer x. So this address, this value was passed for the parameter a. So this value then gets copied into the value of a. And since pointer x is a pointer, so it stores the address of x, also a is a pointer that points to x, because address of x got copied here. The same happens for the address of y. Also, this value gets copied here, so the b is pointing to the address of y. And what did you add now additionally? We additionally have this integer pointer temp. If we maybe switch to the code again, so this integer pointer temp equals a. So the temp pointer has the same value as the variable a. So temp also stores the address of x. So we have also the arrow here from temp to x. And now what happens if we now change or swap a and b, then basically we simply swap the values that are contained here, which are the addresses. So after the swap operation, a contains the address of y, and b contains the address of b. No, b contains the address of x. So this pointer points to x, this pointer points to y, but we only changed the addresses here on the right-hand side, and nothing was changed in the main function. For this reason, we do not perform a swap operation here. And basically, it's still the same concept. It's still called by value. We just copied addresses to the right-hand side. Then we modified there on the right-hand side something in the swap function, but the changes we did in the right-hand side didn't get passed to the main function in any way. And for this reason, the swap didn't do anything.
Yeah, so basically maybe what's also important to highlight one more time, because before we said we have two, if we do pass by value, we have 2 copies of something in memory. Because we did it with the pointers directly and we didn't actually we technically did a pass by reference, if you think about it, that we tried to access these variables, but we didn't actually try to access the values of the variables or change them in any way. All we did was just copy the pointers over, switch them around a little bit, and then just go back again. So we just made extra pointers that didn't actually do anything. So if we just use it this way, then even the pointers won't be able to help us.
And the pointer variables itself got treated as a call by value because they were copied. So we have now a copy of address of X on the right hand side and of address of Y on the right hand side. So this is always a call by value. And we want to call this call by reference now. And yeah, we need to fix this now in some way. So maybe you can do this.
Exactly. Okay,
yeah, so at the end.
This is so all we need to change would be now that we do not use a pointer here. We don't work with pointers in here anymore, but we say we really want to actually modify the values that we have through the pointers we're passing. And we can change, I think I had it on the slide as well. You may have seen this already, but in order to dereference a pointer, so to go from like the address level of a pointer to the thing it's actually pointing at. So in our case, this would be, since we had a pointer, this pointer X here, it's pointing to the variable X. So if we put this pointer star here, so this asterisk, that means we actually access the value this pointer is pointing at, so to speak, which means if we pass this pointer here, that means we're actually accessing the 2 that is saved at the location of variable X. So basically, this is what we want to do now. We want to actively access the variables the pointers are pointing at and swap those around. That should be everything.
So, again, the question, who thinks it is still unchanged, the swap didn't work again? And who thinks it did work now finally? Okay, now most of the people say yes, it works.
And as we can see, 3 and 2 were actually swapped around. And do remember, the only thing we changed in this case from the previous example that didn't work at all and this one was that instead of we work purely with pointers and also make this temp variable an integer pointer, was that we just access the variables here directly. So it's a very small difference between using pointers correctly and just doing anything that doesn't work at all. So do be mindful of that.
Okay, then let's again visualize this to make this more understandable. So this is the starting point now. We again pass the value of the address of X into the parameter A, which is again the pointer. The same holds true for the pointer Y. So again, the address of Y gets copied to the pointer B. So those two store the addresses now. And how does the temp variable get the value 2? In the code you said you dereference A and assign it then to the temp variable. Dereferencing means in this case you go to the variable A and the star operation goes along the arrow that I draw here to the variable that is located here, and the value that is stored into this variable, this is then the value that we access and that we store in temp. Then in the next step of the code, just to recall this, we said star A equals star B. So the value which is stored at the address where B points to gets assigned to the location where A points to. So this means we take the address that is stored in B, follow the arrow, see, okay, at this location the value 3 is stored. We take this value and store it in dereferencing of A. So we take A, go along the arrow and store the value in this variable. And that's why we get the 3 here. And then in the last step, we take the value of the temporary variable, follow the pointer that is stored in B, the address that is stored in B, go again along the arrow and store the value 2 in this memory location. And now finally, if this swap function part gets removed, of course, A and B in a temp variable disappear, but we actually modified the values of x and y from the main function, and that is why this swap really persists now after the swap function is done. That is the magic behind.
So
maybe before we continue, any questions regarding this? So when we call the function, so that's a good question. Yeah, just to cover this as well. Here we don't have any asterisks because pointer x is a variable of type integer pointer. And the expected value of the swap function here is also an integer pointer. So this is basically the same as if you pass an integer to an integer. You don't do any address of or dereferencing. So that is why we also pass this variable directly to the integer pointer a here because they're of the same type.
What you could, however, also do, just to also cover that, we could, because we can see here, we set our integer pointer x to the address of x. We've already seen this operator, and you've already heard about it concerning pointers as well. This is how we get sort of to the address of a certain variable. So what we could also do to turn our x and our y directly into a pointer is that we just directly pass this to the function. So this is also technically an integer pointer because we're taking the address of an integer variable, which is exactly what the pointer stores.
Maybe to come back to your question also for a second, if we would write dereferencing pointer x here, what would this mean now? If we go to the visualization, this would mean we take the address, which is stored in pointer x, follow the arrow here, and then we get to the value 3, and we would pass the 3 to the function. But the function doesn't expect an integer, it expects a pointer, an address. So that's why we really pass the address of x directly.
And of course, that's not possible because the function takes pointers. But if you were to pass it like this to, let's say, just a regular integer function, you would be back at a call by value again. Because you're now just passing like the 2 or the 3 once more.
Okay, so
exactly.
So far we have seen if we just have integers parameters, it is called by value. Basically, we always copy the thing that we pass to the function, by value. So this is always a copy. But if we pass the pointers, dereference them, then we go back to the original variables and can modify them. And then we call this call by reference. So the problem is it's not that easy. Now we have much more cases that can happen, and maybe you start with the next one.
Yeah, because as we've noticed, we've also had this array down here that hasn't really done anything yet. So how about we just kind of scrap the swap function we had, and we say we write a different function. Since it fits better, we say we want to switch two values that we have in an array just with each other. So let's call that flip elements. And now we don't need 2 parameters anymore. we just want to pass an array, and we're just going to pass this how we've learned, like this with our array brackets. And now we, of course, don't have variable a and b anymore. But let's just say, because before we were trying to swap the values 2 and 3, which are at index 1 and 2 of our array here, that we just try to do that again. And let's call this array actually. And we save the value that we have in our array at the index 1 into the temp variable. And as we did before, we then overwrite this with the variable at index 2 in the array, which is the 3. And then we put in there, once again, the temp variable. So this is now basically what we've done before, just a little bit different. Now we just need to call this again. We just do flip elements, and we give that just the array that we've created.
Mm-hmm.
And then we maybe also change the print a little bit, because now we're not talking about x and y anymore, but now we're talking about, I keep saying numbers.
But you can write numbers as well.
Yeah.
I have it in the drawing as well with numbers, so it doesn't matter.
D, and then we do, for the sake of consistency, I need to keep it consistent in the print at least. There we go. And then here, once again, we're not working with x and y anymore, but we're working with array at our index 1 and array at our index 2. So what we've done now is, once again, we have our array down here. We're passing the array to our function up here. And we're trying to swap these two values in the function. Now, who thinks this is going to change anything in the main?
So it changes, yeah? Who thinks it changes?
And who thinks it changes, yeah? Who thinks it doesn't change?
More people for it changes.
Mm-hmm.
Then let's try it out. Okay, so
That
array
changed.
at 1 is 3, array 2 is 2, so they in fact changed. Okay, but we didn't write any pointer star here, so...
Yeah, we just passed the array.
So let's have a look at the visualization.
What happened?
Yeah, so again, we just abbreviated this now with the flip. The flip function is called, and then the array variable here, that is the parameter of the flip function. If it is an array, it will not be copied. We just get the address of the array. So this basically is very closely related to a pointer, and it just stores the address of numbers. So if we follow the arrow along, we get basically to the first element of the array numbers. The temp variable is the same as usual, and then if we do the swapping here, we go to address of numbers, then go to the position 1 and assign it with the value in position 2. So this was the first part here. Array at 1 is array at 2. So we do this in the original array. Then we store the value that was stored in the temp variable at position 2 in the array. And as you can see, now we indeed modified the array here. Here we do not have the array at all. We just have the address of the array. So if the flip function terminates, the change really persists in the main function. And yeah, basically we did a call by reference now with the array. So if we pass an ordinary local variable as an integer, as a character, it gets copied. But if we pass the array now, we really refer to the original array in the main function, so we have call by reference. Here's the question. Okay, so the question basically is, why do we use the swap or the flip function basically? When do we need this in practice? I mean, you probably won't write a swap function in practice in this form, but basically the goal is here to demonstrate you want to change variables that are actually contained in another function. So variables that live in the main function, you pass them to another function. In the other function, you do some computation, you read in some input, you do prints, whatever. You have a large thing happening there. You get a result, and you want to be able to store the result that you computed in the other function. You want to put it also in the main function here. And one instance would be you pass here an array which is uninitialized to an input function, and then the input function reads something from the user, and you want to store the user input into the array, and it is necessary to talk whether you store it just in a local array in this function and the main function will never get the result, or whether we directly store it into the main function. So basically this is, you don't use it within swap, but you use it like in all your further assignments, this concept.
You also need to consider that this is just a really small use case just to demonstrate you how this works. If you, as Michael said, think of further assignments or further programs that you will program in the further course of your degree program, they will get longer, they will get more complicated, and we do still have the fact that something like this only lives within a certain scope, but you can't make a function, let's say 200 lines long, just because you have to do so many operations with something. So that's why it's efficient to think about if you can just pass it by reference to something else and operate on those values, and then just directly change them in the other context. So that's also, so for example, if you have a really complicated sorting function, like if you have an array of values, you want to sort those after a really complicated algorithm, it's efficient to just pass that array by reference to a function, let the function do the sorting, and when you get back from the function, you have a sorted array, for example.
So basically we have now seen in the visualization that this array parameter that we have in flips elements is, I draw it as a pointer. So
why don't we just
write
use
a
pointer,
here.
right? Shouldn't make that much of a difference, or maybe it does. Who thinks this makes a difference?
I need to raise my hand all the time.
I always forget to raise my hand all the time.
Okay, so yeah, some think that there is a difference. Who thinks there is no difference? Okay.
Let's have a look.
Let's see whether it compiles.
Oh, it compiles. And yeah, still swaps the values.
So
interesting.
It seems there is no difference. And if you go back to my visualization, yeah, I don't have an extra visualization for that, because this is, in this case, this is actually entirely the same. Whether we write the parentheses in the function parameter and say it's like an array, or whether we say it is a pointer, it doesn't make a difference in the function call. So it as a parameter here, it doesn't make a difference which of the two things we write down. Also in this case, the integer pointer that we have points to the first element in the array. So maybe if I go back to the previous visualization, like this address of numbers, this is a pointer, it points to the first element in the array. So it is really entirely the same. Only in this case, that's a function parameter, but as a function parameter, this is the same.
So you may have already been using a pointer at some point without knowing that you did, if you passed an array this way. So,
yeah.
You mean in this case in particular as a perimeter? I would say that's basically just syntactic sugar, you could say. I mean, what you can do, which I don't think you can do with the asterisk, we've already heard in the lecture, we can put the size of our array into the perimeter list. And if we then call like a size of operation within the function, we actually get the size of the array.
No, we don't get it.
We don't get it?
No, we don't get it. So this, even if you specify the size here, there is no benefit of
Really?
that.
Oh.
Yeah, I discussed it also with Julia. Also, I said the wrong thing. So basically, there is no advantage in using the brackets. Independent if you specify a size. If you don't specify a size, you can just write always the pointer there. I hope I didn't destroy your world now.
No, that's completely fine.
So basically C does always the same thing here.
So as we already said, using integer asterisk array, same as this, both are pointers. And one important thing, since we've seen both of these ways, just like this in the perimeter list with a regular array, we actually cannot pass the array by value, but it will be by reference. There's ways to circumvent it technically, which we will probably discuss in the future, but not today. But if you just do it like this, like if we just have a regular array that we want to pass to a function, we pass it like this, we expect either this with the brackets here or a pointer with the asterisk, it will be a pass by reference. Right. So what we can also, what maybe you were wondering as well, since we just passed like the array here, like just the name of the array, and that's already a pointer. Like that doesn't look anything like a pointer technically. Why does that work? And why do we not need the address of operator that we saw before with the x and the y variables, for example? Well, that's because the name of the array can sort of be used as an expression to point to it, as we've seen. So if we just pass like the array as our function perimeter, as we've done over here, this will just pass a pointer to the function that directly points at the first element of the array, even though we haven't really used any type of notation here that this is a pointer technically. And if we were to dereference this name of the array, it will print 1, which we will also see in a second. Let me just add that up here as a little printf.
Yeah, just print the value directly.
Yeah, then let's do that as well. And then we just do this asterisk array. And then just for completion's sake, let's also already compare that to the first value of the array, because that we would do that with array at position 0. A bit too small to see. So we can see if we just dereference the array perimeter that we got here, that this really is sort of its own type of pointer, even though we've just passed technically the name of the array, right? This does indeed point to the first element of the array, because if we dereference it and we print the value, we get the 1, which is the same as if we print the value at the index 0, aka our first value of the array down here. So if we maybe have a look at that in the visualization again.
Yeah, so this is now many things happening. Maybe let's go back to the previous visualization to make it a bit easier. So we said this array is the address of numbers, and if you forget on the left-hand side that this is an array, forget this for a moment. What is on the right-hand side? It is just an integer pointer that contains an address here. Because we don't know that there was an array, it just contains an address. The type is integer pointer. Is there an array? Is there no array? We don't know. So if we take this as a pointer, go to the address. Yeah, this is then this address here, this place here. Dereference it. We look at the address. What value is written there? It is the 1. Okay, so this is one thing how we can think about it. But we can also think about the pointer as an array and say, okay, this stores the start of the array, so this is here. And if I now go to the 0th position of the array, basically, I go directly to this value and have a look at this value. So this is really the same thing. And now, in the second visualization here that I have, I have it called now numbers. I'm sorry, now we changed it to array. I mean now this, the array variable here in the main function. I just talk about the main function at the moment. This is now basically, this is an array, we have learned this. But if we pass it here, then it certainly becomes a pointer. So what is the relation here? So you can basically think that the name of the array, so in the code it's array, here it is numbers, doesn't matter, that this is kind of a pointer which points to the first position of the array. But this is not an actual variable that is stored in the memory of the program as the pointer x or the pointer y is. This is just a name that we can use in our program, that we can refer to the array. So we could say this is kind of a fictional pointer here, which does not really exist in our program, but it's just a name that we can use that we go to the array. And since this is a pointer pointing like to the 0th position of the array, if we pass this name to a function, okay, it's here, yeah. If we pass this this fictional pointer to a function, then we have the parameter inside of the parameter, the same address is stored, and the same address means that this now real actual pointer that exists points to the same location as this fictional pointer or this name numbers points to, which is the start of the array. And that's, I mean, this is a bit tough maybe, but really this is the name of the array, but in the background it says, okay, where does the array start? Okay, here. And if I pass this name to a pointer, if I want to store basically this as in a pointer or pass it to a function, then I create the pointer that points to the first element in the array. I know this is a lot, but I hope this helps understanding when we visualize this, what is really happening in the memory here. And that's the relationship between the arrays and the pointers. Like an array is very similar to a pointer that points to the first position of the array.
Are there any questions on that for now? So you will hear more about this in the lecture as well. And once the practical and the lecture are over, really just take some time and think about this again. I promise you, if you try it out a few ways, maybe on your own with some small C examples, or you go through these examples again in maybe 2 or 3 days, it's going to make more sense. It's just a lot for now. So I think we need to skip this.
Yeah, we skipped this chapter, so we will
Sad.
postpone this to next week. And
Next time.
Go to the reading and input part.
Yeah, so today we'll also talk in the last 15 minutes about fgetS, getchar, and what end of file means, which will also be relevant to assignment 2.
I think we come now to your favorite slide.
Yeah, which is that we have to say goodbye to scanf. Sorry, scanf, we won't be using you anymore. You're not our friend. We will now, at least as long as we need to read in strings, we will start working with fgetS and getchar, just because scanf can get really complicated and annoying to deal with when we want to read in arbitrary inputs. And these two are just way safer, basically. So I hope you spend enough time with scanf, because you shouldn't use it anymore, honestly.
Okay, then let's have a look at fgetS. So fgetS, if you look here, this is the function signature of fgetS. So it takes basically 3 parameters, a character pointer. And as we've seen before, pointers are basically very similar to arrays. So think about this, that we pass an array to fgetS, then a size. So this will then refer to how much we will read from the user, and then this file pointer stream. So this is something that we will discuss only in a month. So ignore this in the moment. This would just, if we write here, we will write here something that we can read from the user input. You could also read them from files later on, but we ignore this part. Okay, so let's see what is important. So fgetS reads in at most one less than size characters. So if we specify in the size, for instance, 10, then fgetS would read 9 characters and stores them into the buffer pointed to by S. So buffer means this should not be like a single space or like a single place where we can store something, but many characters. So this means this will be an array then. So for instance, we could have here an array of size 10. And then we specify the size of 10. Okay, then we store at most one less than size. So we'll store 9 characters into the character array S. Moreover, reading stops after a new line. Yeah, so this also makes sense. If I read something from the user, if the first new line encounters, then I don't continue reading from the user because, I mean, then I would like to continue with the program unless I would ask for a second input. If a new line is read, it is stored into the buffer. And now an important thing, a terminating null byte is stored after the last character in the buffer. And that's the reason why we read one less than size characters. So if we can read, if the size of the buffer is 10, we read 9 characters, and then on the 10th place, there is space for this null byte character. So that is fgetS, and maybe that is a bit much, so let's maybe see it in an example. Maybe we switch positions.
Yeah, of course.
Do we have something prepared? No, I don't think so.
Nope, I didn't make a file for that.
No problem. And just continue here. So we said we need to create an array. So we create a buffer, and I make it now a bit smaller that it's even easier to demonstrate this. So this is the array of 5 characters, and I want to read in an user input. So I call fgetS now. Also here it states the parameters again. So the first thing is this character pointer S, where we want to store the input. This will be our buffer. Then the size is 5, as the buffer has size 5. And then this file thing here is, we will now always write stdin for standard input, so that the user actually gets asked for an input. And now I want to do a bit more. So we call the user input, I want to print it as well, and that we see what fgetS did. So we go just over the 5 elements in the array, and I'll just print the buffer at the respective position, and then the element that is contained here. So I need to pass here the I, so that I get buffer 0, buffer 1, buffer 2, and so on. And here I pass in the element that is stored into the buffer.
Maybe a quick in-between question for that. Is the standard input something else than what scanf read from?
No, scanf and stdin is not the same thing. Yeah, so scanf also reads from a standard in. This is what you type in the terminal. And also fgetS, if you specify stdin there, it reads from the terminal. Okay, then maybe let's try this out. You have already prepared compilation, very nice. If we run this, okay, now the program, I don't have a prompt now, but I can enter something like, for instance, hello. And then if I type this, then I see, okay, at the 0th element of our buffer, the H is stored, at the next the E, then an L, and then an L. What is on the last position of the buffer stored? As we've read before, the terminating null byte. As we've said, a string in C always needs to have this terminating null byte at the end. So this last element in the array is reserved for the terminating null byte. Okay, what happened with the remaining part, with the O, and also hit the enter button? So let's see what happens if I just copy the code over and do it a second time. So we have now, we call fgetS basically 2 times. I again type hello. And let's make it a bit larger. Okay, what happened now? So the first part is the same. So we have the H, the E, the L, and the L. And then we got the null byte because we can only store at most 4 characters in this array with the including null byte. And then we did not get asked for a second user input. Why? We talked about this like 2 or 3 weeks ago. When there is still something in the input buffer, so this would mean the O and the \n is still in the input buffer, then the user does not get to enter an input. Instead, the remaining parts of the input buffer are taken. So in the second call of fgetS, we store then the O into the 0th position of the buffer. Then at the next position, we store the \n. That is why we have this ugly new line here, because we actually print this new line character here somewhere. That's why we have this separation. At the next position, the terminating null byte is stored again, because this marks the end of the string. So the O and the \n were in the input buffer. The \n indicates now the input is over, fgetS does not continue reading, and to terminate the string, this \null character, which is not indicated here, is stored. And the remaining part, buffer 3 and buffer 4, is not touched anymore by the fgetS because we only needed like these first 3 positions. And for that reason, buffer at position 3 still contains the L from the call before, because we didn't overwrite it anymore. We just overwrote the 0, 1s, and 2nd position. So I also have a visualization for that, I think. So I type in hello with the \n, and in the first call to fgetS, I can store the first 4 characters that were in the input together with a null byte that says, here is the string over. Every string needs to contain the null byte at the end, so we need this space here. And then we call fgetS a second time, then the O from hello world, the \n from the input is stored, then we stop, we have reached the \n, we stop reading from the input, and we need to terminate the input again with a null byte, and the remaining part, which is here in gray, is not touched by the second fgetS call. So that's why the L and the \0 remain from the previous call to fgetS, because we use the same buffer twice.
What would happen if we read in something that's shorter than the 5 characters, something like a hi, for example?
Yeah, then basically it would refer immediately to the second case, but let's try this out. If I just type hi, then at the 0th position we have the H, at the next position we have the I. Then we have the new line character, because I always need to hit the enter button that I can terminate the input. At the next position, nothing is shown, because here we have the null byte. And at the very last position, we have like this weird symbol here. Why is that? Because fgetS did not overwrite the last symbol, because we only needed the first 4 places in the array. So the 5th place in the array is not touched by fgetS. And at the beginning of our program, something was contained there, and this something is still there, because it doesn't matter.
Yeah. Yeah? Yeah, that's because the array in our case wasn't initialized with anything. So that's why we just have anything in there. It's the same if you just define like integer x, and you don't say integer x like equals 0, and you just use it. There's just some garbage there, you don't know what it is. This is also why initializing arrays is so important. But another important thing to consider, especially here, is that if your input is shorter than what fgetS is reading in, you keep the new line. you may not want to keep the new line. So do be mindful of that in the assignments or something, for example, you may need to, if you use fgetS, look for the new line and replace the new line with the null byte if you don't want to keep it.
Mm-hmm. And one more remark about this, since the input was now shorter than the buffer size, we did not terminate the program, but now the second call to fgetS also waits for an input. So I could again type, now for instance, hey, and in this case now fgetS is called, we store the first 3 characters, then the \n, and that in the end we have also the null byte. Okay, we need one more thing about fgetS.
One more thing about fgetS and hopefully getchar as well, if we get to that. So one thing that you will also see in the assignment now is a concept called EOF, or end of file, which basically means if you can simulate an end of file if you press Control and D in your terminal while running some program that is waiting for an input. And what this does is it basically just terminates the input. And fgetS and getchar can deal with this signal. So if you press Control D while you have a program where fgetS or getchar are waiting for your input, they can actually notice that this is happening and you can react to that in your program. So let's think of it for now as if the input that we're taking is kind of like a file and we're just ending that file. We're saying, okay, we don't want anything else to be written to this. So we also have a nice visualization for this. So once again, we have our hello, but let's just not think of it as the previous program we had, but we now read in more characters as we did before. And the user can keep typing here technically, and we can type WORL because we want to type in hello world. But if we just press Control D right after this first hello, we just kind of kill the input. We say, no, we don't want to do anything else. We don't want to take any more input. So it's just kind of an indicator for that.
It is not only about that you like you get asked for the input and press Control D and okay, this time you don't enter an input, but if you press Control D, you will never be able to enter any input to the program.
So it's really you want to stop completely. Yeah?
Yeah, so
yeah, in this case, yeah. So think of it that this is the first fgetS where we read something, and then we could start typing WORL, but if we then press Control D, we just kill everything.
So we have like 2 user inputs consequently, one where we type the hello, and then for the second input, we either continue with world or we press this Control D.
Could actually check what happens here if we try that.
Yeah, let's try it.
So we say we want to, let's just start with hi, and now I'm pressing Control D. It's just kind of dying.
Yeah, because we did not handle it at all. So let's imagine if we type hi.
Yeah, and we do like...
No, but let's continue.
Yeah, okay.
So for the input, for the first input, it would be hi. For the second input, it would be Control D. But we don't handle this case. Yeah? We see basically that after the second fgetS, we still have the hi contained in the buffer. So nothing changed. What did the second fgetS do in this case?
It basically just reacted to the fact that we entered Control D. It said, oh, okay, you want to not do anything anymore? Okay. And then we just immediately proceeded to the second print again, which just prints, yeah, the same thing as we had before because nothing changed. And to be more concrete about what actually fgetS returned, because fgetS does return a value when it registers that you encountered an end of file, it returns null, which means generally we've already heard that it returns a char pointer. But if this return value is a null, then we can actually register, okay, this was an end of file, you don't want to continue inputting anything. So with fgetS, we can actually react to this end of file.
Should we include this in the program very briefly? Should I write? Maybe
Yeah.
let's continue. Put this in here. So check this for the second fgetS, which I write here the return value of fgetS, and if the return value equals null, then maybe just terminate the program, let's say with return 1, yeah, like there's an error occurring. And now, if we run the program, and now we enter for the first input high as
We
usual.
do the high again. Then for the...
So we have the high contained in the buffer.
Oh, interesting. We actually have a readable character in the garbage. And now we do Control D, and it ends cleanly.
Yeah, so the buffer, it doesn't get printed anymore because we terminated the program earlier.
Because basically we just exited here. So this is also why you can't see the second print anymore, because we never got down here. We just escaped from the return 1. Okay. Now just really briefly, because we're already a little bit over time.
But last time we had the bonus of 10 minutes.
True. Getchar can also react to that, as we've said. Getchar also returns end of file, but in the case of getchar, since it returns an integer, it actually returns -1 and not null, since what we've had with fgetS. So basically we need to use integer, even though we're reading characters, for the return value here, because otherwise we can't store the -1, and that's how we can also react to that with getchar. So we can also have a look at that real quick.
Maybe now.
So if we just do, I'll just
put
look
it.
nice. Yeah, I'll just put it up here. So we set integer c equals getchar. So we just read a single character here. And we're saying if the c equals -1, whoops, then let's make it look a little bit different from the other one, just so we can differentiate between them. We'll just call it getchar EOF. Maybe put a new line there.
Maybe also
Then
return directly.
Maybe let's return like with a 2 here, just to have some kind of difference between them. Doesn't make a lot of sense now, but that's not the point. We again do the high. We're waiting for a character. This is now getchar waiting for a character. And we'll do Control D again. And we encountered the getchar end of file. This is basically the same thing as with fgetS, just 2 different input functions being able to react to a certain signal, which is this end of file, and they have their respective return values when they realize, oh, you don't want to continue inputting anything, which is null for fgetS and -1 for getchar.
And just to highlight this again, it is really important that this is now an integer and not a character. It seems a bit awkward now, you call getchar, but the return value of getchar is an integer.
And we also discussed last week that characters can only take values from 0 to 255. If you don't remember that, please have a look at last week's practicals. And if we just put int here, we're automatically taking a signed integer, which means we can take positive and negative numbers. So this is why it's important that you also specify the correct type here.
And if you know that you have a character, then of course you can store the value that is contained in C, then afterwards also in the appropriate character.
No, oops.
Okay, and like one thing, I just saw one thing here. You can, instead of -1, you can also write directly EOF. So EOF is a constant as you have defined it in assignment 1, hopefully, for the value -1. If we just type this and hover over it, maybe then you should see it is just defined to be -1.
And it even says this value returned by fgetC, which isn't quite fgetS, but fgetS is for string, fgetC is for char. You can think of it like that. And similar functions indicate end of file. So even your IDE is going to tell you that.
Okay, yeah, then.
Yeah, I don't think we can get to any coding anymore. You have to keep that for next week.
Then we switch to the summary. So we have not seen everything that is written here, but we have seen the most important things for A2, which were the multiple files and then also the user input. And we started talking about the pointers, the call by value, call by reference stuff with the visualizations. I hope this makes it a bit easier for you to understand this. And we will continue with this topic also next week. We have even further visualization. We have even more cases. And I hope it helps you that you understand what is happening here. Because if you just see the code and there are stars and brackets, then maybe it's not entirely clear what's happening, but maybe with the visualization it gets a bit easier. Okay.
All right. Then thank you very much for your attention and good luck with A2. Don't forget to register for the coding session and we'll continue with the lecture in, I guess, 8 minutes.
Mm-hmm.